So now that we have seen the formation of these complex ions and the different structures that they form and the possibilities that it offers for different kinds of isomers, it's time to tackle the question, well, how do these things form and why? All right, so we're going to go there now. And for this, we're going to have to go back to our uh, ideas that we discussed in our first semester general chemistry class. So when we talked about bonding, one of the things you probably remember is that there is no one singular theory that explains everything. There is one called valence bond theory that says that when two atoms form a bond, their valence electrons essentially participate by the overlap of atomic or hybrid orbitals. And this is an excellent theory for explaining the geometry of molecules. There's another theory, the molecular orbital theory, that says that the electrons become delocalized into these molecular orbitals. And so all of the electrons are placed in these. Molecular orbital theory explains magnetic properties of molecules much better than valence bond theory, and even explains the existence of molecules that don't seem to fit into the pattern of the valence bond theory. With transition metals, you have electrons in d orbitals that are going to be playing a significant role. Now, here's what is interesting. As far as our understanding goes, the way these complex ions are formed is not by using the metal ions d electrons and overlapping them with orbitals of the donor atoms. That is not the way it works. If you remember, in any given atom where there are d orbitals, where you get to have a 3D or 4D or 5D subshell, there are 5 different kinds of these orbitals. And they have weird names: DZ2, DXY, DYZ, I'm sorry, DZ squared, I'm sorry, DX squared minus Y squared. Forget about the origins of this. What this picture shows us is, if I were to place the donor atoms of an octahedral complex, which you see on the top left there, if I try to put them on top, overlay them on top of the d orbitals of the central cation, you can see that there are 2 of those sets of orbitals that are going to get in the way of the positions of the donor atoms at those corners, either the top and bottom corner, or in this picture here, the one on the left and one on the right here. I'm talking about the top right model, the dx squared minus y squared, right? This one over here and this one over here. You can see where there is a potential for conflict at these positions here, where the orbitals, the clouds of electrons that are there, could repel the incoming donor atom. Remember, we're not proposing that the donor atom forms a bond by overlapping with the d orbitals of the central cation. What we propose is that the central cation is simply a region of very high positive charge density, and the incoming donor atoms essentially behave as negative point charges, and they are drawn into a semi-ionic bond with that central that central uh, cation, I'm sorry. All right, so it's not an ionic bond because the incoming donor atom is not really being drawn into some kind of crystal structure with the central cation. It's not a covalent bond because they're not overlapping orbitals. It's simply a type of charge interaction between the lone pairs on the donor atom and the highly densely concentrated positive charge of the central ion. Now, what happens is the d orbitals of the central cation can get in the way. Now, let me go back to our friend Professor Dave here, and let's see what he's got to say. I'm going to come back here to our thing here, and I'm going to let him explain it a little better than I can. All right, and here we go.
I want to tell you about crystal field theory.
He knows a lot about the science stuff. Professor Dave explains.
As we just learned, coordination compounds have some very interesting geometries, and many of these can't be explained using the same models that we use for normal covalent compounds, like VSEPR theory or valence bond theory, since the type of bonding involved is more complex than mere overlapping of hybridized orbitals. Instead, we have to use another model called crystal field theory. So let's go through the finer points of this theory now. Crystal field theory is based on the premise that the metal ion and the ligands can be treated as point charges, and the spatial arrangement of these point charges will affect the energies of the d orbitals for the central metal atom. These are the orbitals that ligands donate electron density into, so these are the chief concern for the model. And this model, although incomplete, just like VSEPR theory,
All right, here we go.
they are donating to the metal ion, and this electron density will repel existing electron density on the metal ion. Due to this repulsion, the energy of certain d orbitals will be increased, and not in an equal manner. To understand why, let's look at this octahedral complex, a very common geometry for coordination compounds. The central metal atom has valence electrons in these d orbitals, which when unhybridized look like this. We must note that two of the d orbitals, the dx squared minus y squared and the dz squared orbitals, have lobes that extend on the x, y, and z axes, meaning that electron density is sitting on these axes. Whereas the other three orbitals have lobes that sit in between the axes. Looking at the octahedral complex, the bonds to the ligands also sit on these axes, which means that in order for ligands to approach the metal atom, their point charges must repel the electron density in these two orbitals. For this reason, whereas for an isolated metal atom, the d orbitals all have the same energy, in an octahedral complex, these two orbitals we mentioned have a higher energy as they point in the direction of ligands, and we refer to them as the Eg orbitals, while the other three are the T2G orbitals, which point in between ligands. The difference in energy between these two sets of orbitals is called the crystal field splitting energy. The magnitude of this energy gap will depend on whether the orbitals involved are 3d, 4d, or 5d orbitals, as well as the identity of the ligands themselves, with the impact following this trend here, called the spectrochemical series. On the left we have weak field ligands, and on the right, strong field ligands. Let's put this into context. For an isolated metal atom, once again, all the orbitals are of equal energy. If the metal is participating in a complex with weak field ligands, the difference in energy is small and not enough to overcome the pairing energy, or the repulsion generated by doubling up electrons in an orbital. In such a case, they will spread out evenly, putting unpaired electrons in the Eg orbitals before the T2G orbitals are completely full. These are called high-spin complexes. But if in a complex with strong field ligands, the difference in energy is very great. In such a case, the system will be at a lower energy by simply doubling up electrons in the lower energy T2G orbitals. These are called low-spin complexes.
Okay, let's go ahead and come back here. So let me walk you through this whole thing again using our PowerPoints here. And we're going to look at some of the things that are affected when we look at this theory. So once more, let's consider that in the absence of any ligands, all of the d orbitals are going to be equal in energy. But in the presence of a ligand, because two of those d orbitals interfere or repel the electron density of the incoming donor atom, they go into a higher energy state. And that is what is the theory here, all right? So basically, we would say that the isolated transition metal atom, all of the orbitals have the same energy. But in the bonded, in other words, in the complex ion, the d orbitals of the transition metal are going to have different energies. We call the higher energy group of orbitals the EG set, and the lower one, we call it the T2G set. Sometimes people just call them the E and the T sets, simply like that. And what is important is that the difference in energy between those two sets is what we call the crystal field splitting. And we use the letter delta, the Greek letter delta for it. Is the energy difference between the two sets of d orbitals in the metal atom when the ligands are present. Again, remember, the ligands donor atoms are not overlapping orbitals with any of these d orbitals. They are simply acting as a point charge that is drawn to the positive charge of the metal. And the only role these d orbitals play is whether they get in the way or not of that interaction. If they get in the way, then you have a higher energy, in other words, a less stable situation. Now, one of the things that we've mentioned several times that you've observed in class is, and in labs, is that solutions of these ions typically have interesting colors. Here is a sequence of solutions that have ions from the fourth period transition metals, going from left to right, from titanium all the way through our friend, the copper 2 ions, which we know have a blue color. And other ones you might have seen before, like the green nickel 2 ions, the pink cobalt 2 ions, right? So let's see how this happens. Now, originally, I used to have a video for this, but I think I lost access. They took my license away to access it. So I'm just going to try to explain it myself. Okay, let's consider a complex ion formed between titanium and water. So this would be titanium with 6 water molecules and a +3 charge. One of the things that we have to kind of like get reacquainted with is the skill of figuring out how many electrons do we have here to deal with. So let's look at titanium here on the periodic table. There it is. It's atomic number 22. But what's important is the configuration of it. Remember that the way we do these configurations is essentially we start out with the basic configuration or the foundation or the what we call sometimes the inner core, which would be like 18 electrons like argon, and then you have 4 more electrons to add in. Okay, numbers 19 and 20 go into the 4s subshell, and then you have 2 more electrons that go into the 3d subshell. So our configuration would be, core of argon 4s2 3d2. The ion we're talking about, though, is titanium 3. It's a +3. And remember that with transition metals, when you start removing electrons, you don't start from the d orbitals, we start from the s orbitals. So the actual configuration of the titanium 3 ion is actually argon 3d1. In other words, this particular ion has 1 electron in the d subshell. Okay? Let me give you a few seconds to kind of absorb that. You gotta remember how to do these things, right? From Chem 1A. Okay, so now let's say that we have our titanium 3 ion in a complex with water. And what the water ligand does, it splits, right? It splits the 2 levels here. You have a crystal splitting effect happening here. Now let's say that light shines on this complex. Light comes in the form of photons of certain energy given by the Planck equation, H times the frequency. And that energy might be sufficient if the amount of energy is right to excite that single electron, which is now in a lower energy level, into a higher energy level. But that only happens if the photon has the right amount of energy to bridge that crystal field splitting gap. All right. Remember that for most substances, if you do a spectral analysis, you will find they typically have a wavelength at which they have maximum absorbance. Well, that is probably the wavelength that has the kind of energy of light to cause that electron, in the case of titanium, to jump up across the crystal splitting field, the crystal field splitting gap to the higher set, to the E-G orbitals, right? So remember that when we deal with light and absorbance, remember that whatever light a substance absorbs, the color that's going to come through or be reflected will be the one that is complementary to it. And we can use a color wheel for that, except that, again, this one might not be converting the colors very well, but it goes, red, orange. I'm going clockwise. Red, orange, yellow, green, aqua blue, and blue, kind of like purple kind of thing. So it's hard to see the colors here sometimes. And don't forget that in terms of the absorbance here, what we're going to find is what is the wavelength at which you have maximum absorbance, because that is the photon of light that has the right kind of energy given by Planck's equation. H, Planck's constant, times the frequency. All right, so let's do a little practice test here. A complex ion, this is cobalt with ammonia, and the cobalt is +3, occurs at 470 nanometers. A, what is the color of the complex, or let's say the solution where this complex is in, and what is the crystal field splitting in kilojoules per mole? So let's say, for example, how did I make this? Probably I took a cobalt compound and reacted it with ammonia, similar to the lab that you guys are going to be looking at this weekend. But in this case, it's cobalt. In your case, it's going to be copper too. And let's consider then what we're saying here. Let's look at the color wheel. We are saying that the complex absorbs, has a maximum at 470 nanometers. If you look at the color wheel, you can see that this is kind of like in that cyan color, the kind of like sky blue kind of color in the bottom there, between 430, 490 nanometers. So that means that the color you're going to see is the complementary of that, which would be orange. Okay, so that's the way you work it. Whatever color you see is the complement of the color that the substance is absorbing. All right, they're complementary to each other. Okay, question number 2. What is the crystal field splitting in kilojoules per mole? Okay, so remember, the crystal field splitting is whatever that photon of energy was able to provide. So it's Planck's constant times the frequency. But since they gave us the wavelength, let's go ahead and convert that frequency into speed of light divided by the wavelength. H and C are both constants. You can find these, you can Google them, or you can find them in your book in one of the appendices or somewhere in there. But Planck's constant is 6.63 times 10 to the negative 34 joules times seconds. Speed of light, we use the speed of light in a vacuum, 3 times 10 to the 8th meters per second. And we have to use these units so that we can cancel things out properly. And the wavelength is 470 nanometers, but because we want to cancel meters out, we're going to have to convert that into meters. So, a nanometer is 10 to the minus 9th of a meter. So we're going to write it in non-orthodox scientific notation there, 470 times 10 to the negative 9 meters. So I think you should all agree that we're going to properly cancel units here. So the seconds are going to cancel out with seconds in the bottom here, meters in the speed of light with meters down here. So we are left with joules. Put these numbers in the calculator. Careful with the scientific notation and your operations. So 4.23 times 10 to the minus 19 joules. All right. This is the energy in a single photon. In other words, this is the energy applied to the transition across the crystal field splitting gap for one single atom. We want kilojoules per mole, right? So we're going to have to take this guy here, right? Multiply it times 1 kilojoule per 1,000 joules times Avogadro's number. So we can take the atoms out and we can take the joules out, and we're going to end up with units of kilojoules per mole. And I believe our final result would be about 255 kilojoules per mole. All right. Let me give you a few moments there to process all that. You'll notice that I basically brought in Planck's equation there. This is kind of old stuff. If you forgot about it, you can just check it back in. Not exactly sure in Top Hat what chapter that is. I want to say somewhere like maybe chapter 6 or 7, somewhere in there, 8. Okay, so now we see why these particular ions, when you put them in an aqueous solution, of course, what they're doing is they're forming complex ions with water. Most of the time, especially for the period 4 transition metals, these are going to be octahedral complexes, which, as we saw, generate a crystal field splitting into 2 types of d orbitals, the E and the T group. And we can calculate based on the spectrum, on the absorbance spectrum, we can calculate what is the approximate crystal field splitting energy in kilojoules per mole. Cool, right? Now, the other thing that crystal field theory explains is the magnetic properties of these ions. Once more, let's consider an octahedral complex. Again, on the left there, we see the 5 equal energy orbitals of a non-complexed metal cation. And then on the right side, we see the crystal field splitting when you have a ligand attached. Now, how much separation you have between the E and the T orbitals, in other words, how wide that crystal field splitting is, depends on the ligands. And we have what is called a spectrochemical series. I don't want you to memorize this. Just have it handy somewhere, maybe on a note card, or maybe copy this slide somewhere. I think the final exam is going to be open book also, so just know where to find this kind of information. But you will be responsible for at least knowing how to use this spectrochemical series. A spectrochemical series is written in order from left to right, from weak field to strong field ligands. And by weak field, we mean these are ligands that in an octahedral complex will give you a small crystal field splitting, whereas the strong field ligands will give you a large crystal field splitting. By that we mean how far the top 2 orbitals are from the bottom 3 when you have the ligand bound in there. Now, let's consider these scenarios, in terms of the placement of electrons into these particular orbitals. So let's start out with an iron 3 ion, and you should be able, using your periodic table, to tell that an iron 3 ion has 5 d orbital electrons. And of course, based on Hund's rule, we place them in separate orbitals. In other words, they would prefer to stay in separate orbitals where they minimize the repulsion. And we also have all of their spins here unpaired. So by drawing the electrons as arrows, we can show if they are having a plus or a minus spin. And in this case, we're drawing them all with a plus spin. We could draw them all with a minus spin. As long as all 5 of them have the same spin, you should be okay. Okay, let's see what happens if I put iron 3 in a complex with a weak field ligand. Remember, a weak field ligand produces a very small crystal field splitting, like that. So a sample of a weak field ligand would be, let's say, I don't know, the bromide, the chloride, the fluoride ion, one of those guys. So let's say that we're having an iron and fluoride complex. What happens is the difference between the two sets of orbitals is small enough that the atom can still afford to keep the electrons in separate orbitals as it forms the complex ion. In other words, the difference in energy by the crystal field splitting is not that huge, it's not that unsurmountable, and still the atom, quote unquote, prefers to minimize the repulsion that is forced by putting electrons in the same orbitals. And so what happens here is you now have 5 unpaired spin electrons. So this is what we call a high spin complex, because you have many electrons that have unpaired spins in them. Now, what happens if I put the iron 3 ion in a complex with a strong field ligand? Let's say, for example, the cyanide ion. So the cyanide ion is a strong field ligand, which means it produces a broad or a large crystal field splitting, a large gap here, like that. In this case, the difference in energy between the top set of orbitals, or the E group, and the bottom one, the T group, is too big. And so because of that, the atom has to resort to keeping the electrons in that bottom set of orbitals, which means that 2 of those orbitals are going to have to be filled, and therefore you're going to have 4 electrons that have paired spins and only 1 that has an unpaired spin. So in comparison with the complex with the weak field ligand, where we had 5 unpaired spins, in other words, a high spin complex, and the one on the right with a strong field ligand, you have a low spin complex with only 1 unpaired electron spin. So what you can do then is, looking at all the different types of scenarios, these transition metal ions typically form complexes when they have, let's say, 1, 2, 3, maybe 4, 5, I mean, different numbers of electrons. But we are interested in situations where you have more than 3 electrons to place in here. Because as long as you have 3 or less, they're going to stay in the bottom set of orbitals, regardless of whether you have a weak field or a strong field ligand. There's no problem with that. The problem starts when you start having a 4, 5, 6 electrons, because now you are forced to decide, do I pair them up in the low energy d orbitals, or am I able to split them up so they can still occupy higher energy ones? And here are the orbital diagrams, and this is another chart that you probably want to keep a hold of. So the idea here is, how do I use this? Let's say I am given a ion and I'm asking it to form a complex ion with a given ligand. Okay, the first thing I need to find out is, what is the coordination number? Because if the coordination number is 6, then I can use these diagrams. These diagrams are for octahedral complexes only. So in order for that to work, the coordination number has to be 6. There have to be 6 donor atoms, not 6 ligands, 6 donor atoms on that central cation. The next thing I need to find out is what is the oxidation number for that central cation? In other words, what is its charge? Because that's how I determine how many electrons I had to place in these d orbitals. This particular chart, like I said, only covers the scenarios where you have 4, 5, 6, or 7 electrons. Next, what you're going to do is once you have the electron configuration, whether it's D4, D5, D6, or D7, then you're going to find out which of these 4 cases we're into. And next, and last but not least, you're going to decide, is the ligand a weak field or a strong field ligand? If it's a weak field ligand, you're going to be forming what's on the left side, the left column, which will be a high spin complex. But if it's a strong field ligand, you're going to form the low spin complexes on the right. Okay? Okay, let's see if my camera holds up here and we can do a little practice exercise. Let's see if we can make it work. So here is the exercise we're going to try to do here. Once more, let's hope I can get this guy to work. Okay. Oh, here we go. So I think you should have this slide in your PowerPoint. So it says here, what would be the magnetic properties of this complex ion? It's a cobalt with 3 ethylene diamine ligands and a +3 charge. And it tells us that ethylene, oh, that's misspelled. It should be ethylene, it should be an E between the N and the D, is a strong field ligand. Okay, first thing I need to find out is what is the coordination number? Ethylene diamine is bidentate, right? So that means that I have 3 and I have 2 donor atoms per molecule. So that means that my coordination number is 6, and therefore I have an octahedral complex. Now you might wonder at this point, what's the point? What aren't they all octahedral? No, they're not. Not only are they not octahedral, but if they are square planar or tetrahedral or something like that, the crystal field splitting diagram is completely different. Actually, it's actually reversed sometimes. Okay, so that's the first thing we did, find the coordination number. The next thing I want to find out is what is the configuration? Because I need to find out how many electrons am I dealing with in the D subshell. Okay, let's bring our good old periodic table here. And we're dealing with, what do we say here? Cobalt. You can see cobalt here on the right. Atomic number 27. It's in period 4, which means that it has a core of argon. And then it will have 2 electrons in the 4s subshell, and then, oops, sorry, 1, 2, 3, 4, 5, 6, 7 electrons in the D subshell. So let's write that out. So for cobalt, we have core of argon, 4s2, 3d7. So what would it be then for cobalt 3? All right, we don't touch the core electrons, right? We don't touch those. We start out by removing the 4s, and that's 2 of them. And then we need one more off. So we take one of these 3d electrons, which means we're left with a 3d6 configuration. All right. Next. Which diagram are we going to use here? Well, remember, we said that this guy, which we abbreviate EN, the ethylene diamine, is a strong field ligand. That means that when we look at this chart here, we're looking at, okay, who has the strong field ligand? Well, the complex on this side, and it says here for D6, which is what this cobalt ion has, the strong field ligand, the one that produces the broader split, has a low spin complex. As a matter of fact, it is a situation where all the electrons are paired. So this is going to be, whoops, sorry, low spin. We find that all electrons are paired. And I don't know if you guys remember this word, but when you have all of the spins paired, we have something called a diamagnetic atom. All right. That's what we have. In other words, this particular complex will not respond to the presence of an outside magnetic field because all of its electrons spins are paired. All right. Cool. All right, let's look at the next practice exercise we have in here. You have this in your what do you call it, in your handout. I'm gonna let you guys think about this one for a moment. All right, it says a fourth period metal ion in a high spin octahedral complex has 2 more unpaired electrons than the same ion in a low spin octahedral complex. What are some possible metal ions for which this would be possible? Okay, read it a little bit, think about it. Again, we're still in the fourth period. We've kind of like basically focused mainly on fourth period transition metals. I'll talk a little bit more a little bit later at the end about other ones. So how do you think we go about this? Well, let's convert this. First of all, it says that it's octahedral, so we can use that chart. And it says it's in a high spin complex. So we're going to look at something that is essentially a, weak field ligand. And it says it has 2 more unpaired electrons than if you had it in a low spin octahedral complex. All right, so let's look at what are the possibilities here. Come back here to our chart. Let me zoom a little bit. Oops. Can't get it to zoom in. Anyway. There, it's a little better. Okay, remember this is D4, D5, D6, D7. This is the high spin, this is low spin. So we had to find a set here that will have 2 more unpaired electrons than in the low spin. So let's start with the first one here. This one has 4, we would have 4 unpaired electrons in the high spin and 2 in the low spin. So that's a candidate. All right. How about the next one? In the high spin, it has 1, 2, 3, 4, 5. In the low spin, it has 1. So that's not a candidate. D6. 1, 2, 3, 4 unpaired spins in the high spin complex and none in the low spin complex. So that means that one doesn't work. 4 versus 0. D7 has 1, 2, 3 unpaired electrons in the high spin and 1 in the low spin. So that one also works. So let's put an asterisk on both of those. And so we are saying that our candidates, let's come back here. Okay, again, D4 and D7 are our candidates. So our candidates here, oops, zoom back in. Oops, not that much. Our candidates are D4 and D7. So now it's a matter of you finding out what ions in the third period could have a configuration D4. So basically you're talking about this. It has to be AR 3D4 or AR 3D7. So you had to get some metal that when you take electrons away, you end up with one of those configurations. All right. Don't forget that the cobalt 3 that we did last time was 3D6, so that wouldn't work there. So what do you think would work? I'll give you one that I think works. Cobalt 3 doesn't work, but cobalt 2, remember that cobalt was argon, (4s2) 3d7. So if we take only 2 electrons, we would end up with argon. We could take the 4s2 electrons, 3d7. So cobalt 2 could work. And there's a few more that would work. I'll let you kind of work on that later on, okay? Excellent. Okay. Yes, it's challenging. I understand. It is challenging. But a lot of it is because we've forgotten how to do these configurations and how to get these transition metal configurations. That's why I was trying to get you guys to study those materials ahead of time so we could, avoid a bit of the pain here. Okay, we only have a few more minutes, so let me wrap this up by going back to finish our PowerPoint. And I won't be able to give you everything we have in there, unfortunately, because there's a lot of interesting stuff, but I'll let you read about it later on. One of the things that are important is, as we said, what are the factors involved in the properties of a complex ion, right? One of them, once we said, for example, one of them is what is the kind of ligand attached? That's the spectrochemical series. Now, we didn't discuss this, but actually the size of the energy gap can also depend on the type of cation. And typically, as you increase the charge on the metal cation, you also tend to increase the crystal field splitting. Another thing that affects the crystal field splitting is the size of that cation. Notice that we've been essentially talking about period 4 transition metals only. We haven't touched period 5 or period 6. These are bigger atoms. And when you have bigger atoms, those d orbitals might be hard to kind of like work around because they're farther away from that positive charge of that cation. So those kind of things will also affect, all right? The other thing that affects is what type of complex. So you can see here on the left side, I've drawn a cube that would represent essentially the typical octahedral complex. But notice that in this case, we're talking about tetrahedral one. The tetrahedral complex is as if you had a cube and you had the positions of the donor atoms would be where those corners are. There's 4 of the corners inside, looking from inside out of that cube. Remember, the donor atoms are coming in, try to place themselves at positions here. But notice that although none of the d orbitals are actually directly in the way of those 4 positions in the tetrahedral shape, the dxy, dxz, and dyz actually are a little bit closer to those positions. I'm sorry. They're a little farther. I'm sorry. They're a little farther away. They're a little closer. So you're going to have a different kind of splitting here than you had with the octahedral complex. So what happens essentially is that in the tetrahedral complex, you can see here on the right, number one, because you don't have the direct interference where orbitals are positioned exactly where the donor atoms are going to fit in that tetrahedral space, the crystal field splitting is going to be a lot smaller. You can see here on the right side here, you can see how the crystal field splitting is a lot narrower. Not only that, but the placement of the orbitals is reversed. So the 2 orbitals that were higher in energy in the octahedral case are now the ones lower in energy in the tetrahedral case. If you continue this kind of analysis into other types of complexes, for example, square planar or linear complexes, you can see that it gets very interesting. You can have 3, maybe even 4 different types of levels here. In other words, you have more than one crystal field splitting arrangement in here. Typically, transition metals that have big atoms like platinum and things like that, they tend to form these complexes because there's not a whole lot of room to accommodate, 6 donor atoms. And so they go more towards the square planar and the linear structures in here, all right? I'm going to have to skip this part here. I'm going to let you guys read this on your own, this thing about the kinetics of these complexes. Sorry, we don't have time. Just want to remind you about some of the applications that we have of the formation of these complex ions. Number one, many of the processes by which we extract metals from minerals or ores on the earth, where they come in the form of, let's say, ionic forms, we sometimes extract them as cyanide complexes to purify them away from other things. For example, nickel, which is obtained in nickel, ion ores, can be extracted by forming a gas complex with carbon monoxide that can be essentially extracted from the rest of the solids, and then you can purify it that way. Another application of complex ions is what we call the chelating agents, like EDTA, which can be used to remove metals like lead, mercury, and other possible toxic metals. You can read in the textbook about cisplatin. This is the famous so-called cancer treatment that used to be called platinum, but it's actually cisplatin. Notice that it is a coordinate compound of platinum with ammonia and chlorine or chloride ions. Notice that there's no counter ions in this case. There are some coordinate compounds where the actual ligand serves both as ligand as also as counter ion at the same time. And so the cis isomer of this is a flat structure that essentially causes DNA molecules to get cross-linked. And the idea is that rapidly replicating DNA, as in cancer cells, will be more susceptible to it, and that's how you get those cancer cells killed. And of course, you're all familiar with our techniques of qualitative analysis. We've used several reagents that give us a color or precipitate or redissolving type of reaction with particular ions. So for example, we can use dimethyl glyoxime to, or DMG, to distinguish between nickel 2 and palladium 2 ions. As you can see here on the bottom, nickel 2 will form a red complex with DMG, whereas palladium 2 ions will form a yellow complex. And of course, on the top, you have our famous SCN guy. You have the iron 2 SC, I mean the iron 3 SCN complex that gives that red color, right? And you have the, if you do it with cobalt, you're gonna get a blue color in there, all right? Okay, guys, we're going to stop here. Sorry that I don't have time to share more awesome things with you about these incredible chemistry of transition metals, but that's about as far as we're gonna go. Our goal then is to, I guess I ran a little bit over here, so let me stop the recording here. And hopefully this will be ready for you. I'll fix it up. There was a part of the video that got a little glitchy there, so I'll fix that up by the time I post it to Canvas, okay?